Uno, dos, tres. Buenos días a todos. Ok. Bueno, pues vamos a empezar la sesión de esta mañana con el profesor Javier Montaño Domínguez. Adelante. Bueno.
Hola. Hola, buen día. En inglés. Sí. Tenemos personas en línea. ¿En línea? Okay, good morning. I'm going to present you this research. The name is the top quark chromomagnetic dipole moment in the standard model from the four-body vertex function. Okay. I will skip the abstract in order to lead you to the details and to preserve the mystery. Okay. Okay, I'm going to talk about dipolar interactions. This subject started in 1948 with Schwinger when he published the anomalous magnetic dipole moment for the electron. At that time, Schwinger in 1948, he obtained this famous constant expression. We can remember that there exists an experimental deviation later. Schwinger this work this is the contribution. Let's explain why the experimental deviation was happening. The explanation was this. So later we can recognize that in QED, the anomalous magnetic dipole moment was explained by this fact. Okay, this is the leading order. Nowadays, if we want to compute the complete contributions of one loop radiative corrections to this problem, we have to consider another loops also. But anyway, this is the leading one. Okay. This concept of the magnetic dipole moment trivially extrapolates to quantum chromodynamics. Okay, how? Well, simply the corresponding Lagrangian, where here we have the strength field of the photon. Okay, we extrapolate to QCD, and now with quarks, obviously, here we have the gluon tensor. Okay. By analogy with QED, we have this. I will refer to this problem as the three-body dipolar chromoelectromagnetic dipole moment. And okay, by analogy with QED, we recognize that here we have the gluon tensor, and as was made for the photon, with this term here, we can identify this dipolar interaction with its characteristic sigma, Dirac sigma. Okay, at this point, there is no surprises, just an analogy with QED. I repeat, extrapolated. Let's have in mind one fact. This one, where in QED, the group constant is related with the corresponding alpha strong through this. Well, for high energy physics, we can consult the PGD, the particle data group, and we will find this value. This value is known from long time ago. It is obtained, characterized for high energy physics at the scale energy of the mass of the field gauge boson. Okay, we continue. We want to perform these computations, okay, following the QED case, but here we have the complete set of standard model contributions. Okay, this one is, I call this Schwinger type diagram because virtually we have the photon. Another similar case is this one. Virtually we have a gluon. Okay, this is the sum of all the contributions. And well, the last diagram with a non-abelian triple gluon vertex has a surprise for the gluon and shell. I mean this one. This will give you a big surprise. I repeat, this Feynman rule or coupling, three gluons. This is an exclusive term coming from QCD. There is no analogy of three gluon or three photons in QED. Okay, a little background on this kind of subjects. For the case, the chromodipole for the top quark has been searched in the context of an effective Lagrangian at the tree level only. I mean, with this kind of diagrams at the tree level, considering this kind of interaction, but in the effective sense, consider it in these points. For example, considering here, or here, or here. Well, I remember, okay, from this reference, we can find this kind of cross sections, which include the dipolar term. Okay, well, this was the case for the effective considerations in cross sections. Okay. Later, in 2008, this collaboration, by the first time, considered the complete set of quantum fluctuations in the context of the standard model. Now, they reported for this diagram, they reported a finite term, but that wasn't correct. In fact, as we will see, obviously the analogy coming from QED for this QCD case, as was the gluon on QED, Q squared equals 0. Obviously, the analogy invites to consider for the gluon on shell, Q squared equals 0. But in that special diagram, in fact, when we evaluate Q squared equals 0, develops an infrared divergence. Okay. Who was the first who realizes that that diagram has an infrared divergence? this collaboration from India found for that special diagram, problematic diagram, found that that term is proportional to this expression, which we cannot evaluate at zero. It develops an infrared divergence. It was made with the Passarino, with the Feynman parameterization. Later, this collaboration from, well, this professor, Bashir, and is from Universidad Michoacana, and other colleagues are from other universities. Well, they follow this reference. This mathematical reference was from 2001, and in 2018, 17, they take these theoretical results, and they made the phenomenology, and they can identify this kind of term of which is clear that if we evaluate from that special diagram Q squared equals 0, that knowledge infrared divergence. So when during many years, this reference was considered by the community as the complete and correct reference in the standard model for this top quark chromomagnetic dipole moment. But okay, then at some point that I was preparing those diagrams for teaching in class, and when then I realized that I have a problem here. Then I found these two reference, that one from India and this other one. And okay, what do we have here? A problem, okay, that, okay. Despite this collaboration, was the first who found that the infrared divergence. Anyway, in that special diagrams, and not only there, in other contributions also, they have algebraic and numerical mistakes. Okay, well, this collaboration was devoted to study this case for a small quark, something like the strange quark, and not for the top quark. Okay, well, that lead us to publish in 2018 these values. Q squared 0 is infrared divergent. In that opportunity, we did not presented mathematical details. We just reported this in our work, because this table was a secondary information in the context of the standard model in that reference. Okay, we published this in December 2018, and later, 1 year later, the preprint was the next December in 2019. The preprint of this collaboration reported by the first time an exact value for this chromomagnetic dipole moment. Okay, what do we have here? Here we reported these numbers in the space-like context. Okay, sorry, I do not explain why, but the following. This proposal, the evaluation was because these collaborators from India proposed to evaluate for a high energy scale the dipoles at the typical scale, high energy scale value of the mass of the seed gauge boson. And in the space-like context, if we consider this positive, we are talking about the time-like evaluation. Okay, why space-like? Why would this minus time? Well, it results that this value are always wrong for the angle. These quantities in the standard model are evaluated in the space-like context. They are not evaluated in the time-like context. It is in the space-like. So, okay, let's evaluate this in the space-like context at high energy physics. So we choose this typical value. We follow this suggestion and we obtained this result. The real part offers us this number, the real part. This one is strictly due to the W contribution. Strictly. That and something. Well, another important thing is that this is it is not matching the time-like case. It is not matching with this central value. Okay. As I told you, no analytical details were given in our first publication of these values. Later, finally published in 2021, here we published the analytical details for the problem. In particular, the dimensional regularization of the Passarino-Bellman scalar function, this one, coming from the diagram with the three gluon vertex. And there we show that when we consider q squared equals 0, this scalar B0 develops an infrared divergence. Later, that same year, this collaboration of Professor Tavares confirms our results published in 2018. Okay, this is the problematic diagram. This is its corresponding contribution. This is the problematic Passarino-Bellman problematic term. Look, it is a B0. Obviously, it has an intrinsic ultraviolet term, this one. The other one, sorry. This one corresponds to this one. The blue one corresponds to this. It's intrinsic as a B0, as its intrinsic ultraviolet term, it's here. The pole strictly it's here. Right here, as published by the Professor Bashir, we have this term, this known term. We cannot evaluate this square equals 0. Okay, up to this point, we can appreciate the problem here, but I continue the obsession for proving the corresponding problem of the divergence due to this term, but with dimensional regularization in order to obtain the corresponding infrared pole. Okay, the details, the mathematical details are given in the paper. Okay, look, this is the subtraction here. We have this problematic Q-squared there. But by dimensional regularization, we can strictly prove the infrared pole. And we have to be careful because we cannot set that this equal to 0. These are poles from with different nature. The one is corresponding to the ultraviolet problem. No, sorry, to the ultraviolet nature, and this one to the infrared nature. Because when we are performing the dimensional regularization of the B0, mathematically, the integration space is split in an ultraviolet region and in an infrared region. So, for those who think that this could be 0, let's mathematically, for the ultraviolet pole, we have that this pole is defined positive. And mathematically, the infrared pole is defined negative. So, we attempt to substitute, to consider the corresponding signs, we will obtain a sum, not a minus sign. Okay. Therefore, the equation 9 takes the form completely in the context of dimensional regularization. We can express like this, and here we have an infrared pole, and all the contribution from the problematic diagram takes this form. Okay, it was proved that such contribution has an infrared divergence if we attempt to this limit, Q² to 0. Okay, what were the results? Okay, this Q², okay, where here, the Q², we identified this Q² equal to minus an energy parameter. We plot these results, and in particular, we want to pay attention to the to the mass of the seed, typical high energy scales for some parameters of the standard model. Let's see what happened when we compare with the experimental result. Okay, the red line is the experimental result. The blue line, the vertical blue line, is the energy at the mass of the seed. This is all, here is obviously, is the complete contribution of all the virtual contributions. Obviously, our value is slightly above the experimental report. This is the space-like case. This is the time-like one. The time-like one, here positive, as you can see, it deviates from the experimental value. Okay. Is that all? No. QCD offers more. As I said, we are following an extrapolation from QED to QCD. QCD predicts that the chromomagnetic dipole And sorry, I didn't mention the corresponding chromoelectric dipole is 0. It results 0. Okay, again, the chromomagnetic dipole, the chromoelectric dipole in this QCD case is tell us that they are proportional to the gluon tensor. Okay. For the 3-body case, we focus on these 2 terms. Okay. The non-abelianity of QCD also contains this term. Okay. This gives rise to this prediction. A dipolar four-body vertex. Okay. We have here. It was never commented in the previous literature. So what we can do respect to this? Just ignore it or what? So it was telling me, look for me. And I look for it. These are the standard model contribution to the quantum fluctuation of the 4-body vertex. All of them conforms 73 diagrams in the Feynman-Topf gauge. For example, from 1 to 7 is the virtual. From 1 to 7 is the virtual contribution of gluons. 8, 9, and 10, the photon contribution, etc. Okay. So all of this in order to prove if the chromomagnetic dipole moment obtained from the 3-body vertex can be reproduced from this one. For example, organized, this is the contribution this is the virtual gluon contribution to the problem. We have here scalar Passarino-Bellman functions, the ultraviolet B zeros, etc., some C's, some D zeros, but individually, some scalar C zeros contains infrared poles, like this one, C01, C04, C06, D01, this is D02. They have infrared poles, but okay, how? For example, this teach me a lot, because I was told that a long time ago that any C0 or any D0 will always be finite. That's not true. We find this kind of expressions, for example, in a paper of Ellis. You see red. It's kind of famous paper. And in fact, there is an online page of this subject. Okay. For example, this is 0 contains, in these definitions, contains infrared poles. This D0 also. Let's see, for example, this delta infrared 2. It means this is here, its definition. Okay, it is played with individually scalar functions with the infrared pulse. Nevertheless, after substituting in this expression, all day magically cancels zero. At the end, we have a finite solution. Important. For the Lorentz invariant term S, always when it will be finite if S is different from zero. Again, as in the three-body vertex case, when we consider S equals zero, we will have an infrared divergence. Not only the virtual gluon contribution has this kind of Passarino-Bellman functions, also the contribution for the photon case will have some of those infrared scalar infrared divergence expressions, but when we sum all of them, such infrared divergence will cancel. At this point, we compare the results. The solid line is the three-body vertex result for the chromomagnetic dipole moment of the top quark. This is the real part. The dotted line, this one here, is the real part, but from the whole body vertex. In other words, also has the same shape. These other ones are the imaginary contributions. Also, as in the three-body case, and now for the four-body case, the imaginary parts comes strictly from the diagrams with W gauge bosons. What happened for the time-like case? It's quite irregular. It's quite irregular. Okay, is this like this, or I have a mistake in my code? Well, for my surprise, in the literature, I find that time-like cases for alpha strong and for the weak angle also are irregular. Oh, okay, that kind of behavior, well, again, matches with other cases. Okay. As we can see, only the space-like evaluation is well behaved. Well, finally, these are the results. Here we can appreciate the evaluation exactly at the conventional high energy values of the mass of the seed gauge boson for high energy. We can compare, for example, the total. This is the three-body results. 2.24, here 2.5. Here we have the experimental value. Again, these imaginary parts. We have different signs for the imaginary parts. These come from the W gauge bosons. The time-like case is written here. We can compare in the next. Okay. Here, our evaluation of the three-body vertex case and four-body vertex case for a typical high energy value corner the experimental value. In particular, here we are considering the absolute value, as we can see. This is while the time-like case move away from the experimental value. For example, if we compare, it is essentially 0.03. It is beyond 0.03 respect to the experimental value. So, conclusions. We have derived the chromomagnetic dipole moment for the top quark from the 3 and 4 body vertex functions as predicted by the Lagrangian. The calculation has been made in a process-independent way. This is, for me, that's very important to keep in mind, in a process-independent way, because we work in the vertex function. We are not considering a process case like a collision, nothing like that. Okay, the space-like evaluations will behave. Finally, the experimental value is between the 3 body and 4 body predictions. That's all.
Thank you very much. Are there any questions?
I'm thinking about the question. Why the behavior of the graphs in S equal to MC are different, are not equal?
Well, theoretically, why they are not equal?
Yeah.
Well, it is, I explained that here. Theoretically, it's expected that they should be exactly equal. Okay. Nevertheless, our numerical evaluation, for example, for the real part, they are very close to each other. My goal was to find that they were exactly the same, but in the phenomenological evaluations, we find that they are very near each other, but not exactly the same. Okay.
Okay, but
The theoretical expectation versus the phenomenological fact, we have a little difference.
Okay, but could you return to the previous graphs, please? I mean, in the time-like graph, could be a problem of how can I say, the number of the precision of the values?
No, we are taking, in what cases?
Okay.
We're taking 100 precision digits. Right. So I consider that that's not the case. At the beginning, I was worried because what is happening with the time-like case? But later in the literature, I found that this kind of irregularities occur for alpha strong when evaluated in the time-like regime, or even for the weak angle. Also, there is a region with bad behavior, irregular behavior. So, okay, that's why it's me. I think that this irregular behavior is also occurring in other cases.
Any other question? Are there any questions online? I don't know if anybody's following. So apparently not. So I will take the chance to ask one question. So when you show the calculations for the time-like and space-like, you have this complex part of your result. The complex part, I mean, you have a complex number, so you have the real and the imaginary part. And imaginary. Yes. So my question is, what is the meaning of this imaginary part? And when you compare it with experimental value, you just ignore it, or what do you do?
Okay, thank you. Experimentally, as we see, they only report that result was a fitting from the experimentals. Was a fitting from collected data comparing with cross-section simulations, but in the context of effective Feynman rules considered in this context. Okay. Simulation in this context. They offer us this result. What I can say about the imaginary parts that happening for the 4-body case and the 3-body cases, they arise strictly from the W diagrams. In fact, this collaboration, they did not report the imaginary part. Our imaginary part was confirmed by the collaboration of Professor Tavares. They comment on the work that they also find for the space-like case, imaginary part coming from the W diagrams. Okay, that was great for me. I suspect that, and I cannot blame them. Well, I can bet that they found that, but they maybe considered that was a numerical fluctuation. So, and they do not report that part because this collaboration performed the calculation absolutely in the Feynman parametrization context. I also calculated in that context numerically all the problem. And again, from the W contributions arise the imaginary parts. So what is the meaning of this imaginary part? In general, weight in absorbing parts of like dumping. That's simply in fact, in the literature, in the experimental literature, was the first time that I find this explanation. In general, they can be complex. They may have absorptive imaginary parts.
Okay, I think.
Up to date, the experimental value, I hope in the future we have a more precise experiment. I don't know. It will maintain this the experimental prediction, or will move from there. I don't know. We must wait.
Okay, thank you. All right, another question.
I was wondering, how do you get rid of the infrared and ultraviolet
Sorry,
divergences?
there is a. What? No, you cannot get rid. You here. For example, let me present you only the more simple case of the 3-body vertex case. This is the contribution at Q squared equals 0. Okay, here we have a point. We can appreciate this behavior is growing in the negative axis. You cannot get rid. I don't know, I hope to understand better this in the future. The following. In QCD, for high energies, we know that what we are appreciating here that in fact, this is the coupling, that's okay. But for energies near zero, it develops an infrared divergence. Let's remember what happened with the alpha strong. Alpha strong, as you tend to zero, that grows. Okay, I can say that I am appreciating analogies for this object with alpha strong. We know that alpha strong, when for small values of energy, is an open question. I find in the literature that the community for low energy has 3 results for alpha strong. Infinite, some finite number, and 0. It's an open question. I hope someday to have the opportunity of study low energy problems, because this is for the top quarter. Okay. It is one of my interests. Tend to study low energy problems in order to calculate and I hope predict for small quarks.
Thank you very much. So let's thank the speaker again. So the next talk is gonna be online.
Can you hear me? Hello.
Okay, Mr. Raul, if you could share your screen, we will appreciate it.
Yeah, but can you confirm that you can hear me? Well, can someone tell me if you
We
are
cannot
hearing me?
see your presentation yet. So please try again. All right, we can see it now.
Yeah, but my question is, can you hear me? No one has answered me.
Yeah, we can hear you now. So please go ahead and start with your talk.
Right. Okay, so just first of all, let me try to see if I can. Are you still seeing the slides? Can you see going from 1 to 2?
Yeah, it's all fine. You can start. Thank you.
All right. So, okay. Thanks for inviting me to the local organizing committee. So I will be giving you an overview of the upgrades planned for the plan upgrades for the CMS detector for its preparation for the high luminosity LHC. So first I will start by, let's say, summarizing what the CMS detector is at present. So as you know, the compact muon solenoid is a general purpose detector which has been designed to run at the LHC and among its distinctive features, these are the 4 Tesla superconducting solenoid, which is enclosed inside a 10,000 tons return yoke, which is made by steel, and in this area, the muon detectors from the muon solenoid are implemented, right? So at present, the the CMS detector consists of several systems, like the tracker, which is a silicon tracker. The innermost part is the pixel technology tracker, and the outer tracker is made of strips. Then surrounded this, or in the next layer, we have the electromagnetic calorimeter, the ECAL, which is made of scintillating crystals, lead tungstate. And next layer comes the hadron calorimeter, which is it's a sampling calorimeter made of brass as the passive material and plastic scintillator as the active material, right? So then we have the magnet that I already described, and after that we have the return jog, where the muon systems are implemented. There are 3 technologies, well, now 4, but I will come to this later. But the initial technologies were the CSCs in the end caps, the drift tubes in the barrel region, and the RPCs, which cover both the end cap and the barrel regions and provide redundancy for the triggering, right? So this is the calendar of the LHC. We are now on run 3. We have started this year, and you can see here the plans for the coming years and the preparation for the high luminosity LHC. So for run 3, there has been only a small increase in energy, which compared to run 2. So we went from 13 TeVs to 13.6. So the main improvement in terms of the sensitivity for new physics searches will come from the increase in luminosity. So during the LS3, the long showdown 3, where the LHC will be prepared for the high luminosity stage, then all the objective is to have it upgraded to enable an instantaneous peak luminosities of 5 times 10 to the 34. Nowadays, the LHC is running at 2 times 10 to the 34, well, the units of instantaneous luminosity, which is 2 times the planned, the design luminosity, right? So at the HLHC, we will be running at 5 times to the 10 to the 34, but the ultimate performance scenario is to reach 7.510 times 10 to the 34. This increase in luminosity will be achieved by upgrading the quadruple magnets in the LHC and by the installation of conducting radio frequency cavities in the interaction regions. So all these upgrades for the LHC will allow Atlas and CMS to collect integrated luminosities of the order of 3,000 inverse femtobars or even 4,000 inverse femtobars in the ultimate scenario, and this will be during 10 years of HLHC operation. So the nominal scenario is to operate at a stable level luminosity, level luminosity of 5 times 10 to the 34. This is to limit the pileup, which pileup is the number of collisions in one bunch crossing, and the idea to have this level is to keep this pileup in average fixed to 100 for interactions. But as I said, the ultimate scenario with 7.5 will come with the cost of having 200 collisions per beam crossing in average. So in summary, under these conditions, it is expected that the detectors, especially the inner detectors, have very high occupancy. This will also come with an increase on the radiation levels. We are talking about something about doses up to 12 megagrays with fluences of 2.3 times 10 to the 16 on the innermost part of the TMS detector. So all this environment will require components or detectors that are radiation hard, and also the electronics. So the primary goal of the CMS phase 2 upgrades is to maintain the current excellent performance of the CMS detectors in terms of efficiency, resolution, and background rejection. So some of the key features to recover this CMS performance and to cope with this pile-up is to increase the detector granularity, so we can keep the similar occupancy as now, but also to increase the bandwidth and yes, the bandwidth to accommodate the higher rates, and also improve the trigger capability, right? So also additional implementation of 4D reconstruction, meaning space plus time, will allow us to cope with all this vertex reconstruction in the high pile-up scenario. So this is a slide. Sorry, can you see my slides?
As we can see that your slides.
All right, thank you. So this is this slide is a summary of the planned upgrades. So first of all, the CMS trigger system consists of 2 stages: the hardware, which we call the level 1 trigger, and then a software triggering, which is the high-level trigger. So from the run 3 on, the trigger rates will be limited to 750 kilohertz at the level 1, which is compared to the 100 kilohertz that are now in run 3. And the HLT rate will be kept at 7.5 kilohertz. So the level 1 latency will be increased from something around 4 microseconds to 12.5 microseconds. On the muon chambers, most of the chambers, well, all of the chambers are on the muon system. Sorry, all of the chambers are expected to cope with the HLXC conditions, so they will be maintained, they will be retained. But the front-end electronics of the DTs, RPCs, and CSCs will be replaced with improved versions to deal with the increase in radiation, and to improve the readout speed and performance, right? So new detectors will be installed in the forward region of the muon system using the new technologies of the improved RPCs, but also the gas electron multiplier. On the silicon tracking, the present silicon tracking will be entirely replaced, and the new tracker will extend the pseudo rapidity coverage from 2.4 to 4. And again, this will be radiation hard and will implement higher granularity and will be also compatible with higher data rates. And one important thing is that we will be having tracking information in the level 1 trigger with these updates. For the barrel calorimeters, the ECAL will retain the same crystals and the same readout electronics. But new front-end boards will be installed to deal with the level trigger requirements. Same for the HCAL, the hadronic calorimeter. In the barrel regions, I will say the brass and the scintillator will be kept, and again the front and back end electronics will be upgraded. For the NCAPs, the electromagnetic and hadronic MCAP calorimeters need to be replaced, and a new combined electromagnetic and hadronic calorimeter, which is a sampling calorimeter, will be installed, and the primary active material will be silicon sensors and plastic scintillator in the low occupancy regions. As an additional feature, CMS will be installing timing detector, a minimum ionizing particle detector that will give information on ionizing particles with some think like 30 picoseconds on time resolution, and this will give additional information to reconstruct for to have the timing for the tracks. So there will be also upgrades in the way the luminosity is measured, but I think that this has been already presented during the workshop. So now I will try to give a short summary overview of the upgrades for the specific systems. So the CMS tracker, as the entire CMS tracker has to be replaced before the high luminosity LHC. As if it is not replaced, if this detector is not replaced, it will have significant damage, and the performance will be degraded under the HL-LHC conditions. So the new phase 2 tracker will consist of an inner tracker, which will be based on silicon pixel modules, and an outer tracker, which will be also made from silicon modules with a strip and macropixel sensors. The main requirements for the new tracker are radiation tolerance. So the upgraded tracker have to be fully efficient up to the target luminosity of 4,000 inverse femtobarn, and also having in mind that it will be reaching the fluence for those scenarios. It will also provide an increase in granularity to ensure efficient tracking performance with the high level of pileup expected for the HL-LHC conditions. Something that it is also important to say is that the new tracker will be improving the two track separation, as the present track has limited performance in the track finding when dealing with highly energetic jets. So this will be also one of the features for the upgraded detectors. So in addition to that, the new tracker will be lighter. So this means that there is less material in the tracker compared to the present one, and it has to provide a robust partner recognitions, which means fast and efficient track finding for the high-level trigger. And as I already mentioned, one of the most important features is that now CMS will be using tracker information for the hardware level 1 trigger event selection. And as I said, the new tracker will be increasing the coverage from 2.5 to 4 units of pseudo rapidity. So there are this description of the plan upgrades for the inner tracker. So the inner tracker will be designed. It has been designed to maintain or improve the tracking and vertexing capabilities under the HL-LHC conditions. The new detector, the new inner tracker, will be made of four layers in the barrel, which are known as the tracker barrel pixel detector, 8 small discs on the end caps, which are referred as tracker forward pixel, and 4 large discs per side in the outermost regions, which are called the tracker end cap pixel detector. So one of the important things of this design is that it will offer the possibility to exchange degraded parts of the detector, especially in the first layers. And it will also be easy to install and to be removed from the cavern. So this is one of the things that have been kept in mind on the design. The basic unit of the inner tracker is the pixel module, which you can see from the picture. It comprises a pixel sensor with some readout chips, flex circuit, and everything how can I say, arranged into a mechanical structure. The silicon sensors, as you can see from the pictures, are bonded to the readout chips. And on the top part, you have this density interconnect, which is glued onto the sensor and a wire bonded to the readout chips. And this high density interconnect provides a clock, trigger, and power distributions for the chip, for the readout chips. There are two types of modules, which differs exclusively in the sensor surface and the number of readout chips. We will be having the tracker will have the 1x2 modules for the inner two layers of the barrel pixel, and for the outer parts we will be using the 2x2 modules, as you can see from this picture, right? So the pixel module is these sensors are NMP. The technology is NMP silicon sensors, and they are segmented into pixel size of 25 by 100 squared micrometers. And these modules or sensors are expected to exhibit the required radiation hardness to deliver the desired performance of in terms of occupancy and resolution. So the readout chip will consist. The readout chip, has been designed in a collaboration between Atlas and CMS, and it's being developed in 65 nanometer CMOS technology. And the cell size of these readout chips will be something like around 2,500 square micrometers. On the way the data will be handled, once the trigger event data is collected from the pixel array, this will be done on the chip, on chip, before sending the readout data to the off detector part of the electronics. Right. So for the outer tracker, will be composed of 6 cylindrical barrel layers in the central region and 5 end caps, which are double discs. There are 3 subdetectors, as you can see from the figure on the right, on the top right. They are named tracker barrel, and this will be implemented with pixel strip modules, referred as PS. And the tracker barrel will be implemented using the 2S-strip or 2S modules. Same for the this is the same for the tracker end cap disc, the TDD. So one of the, as I said, more important, let's say, features of the new detector is that there will be additional information to the level 1 trigger from the tracker. So this has been this has been driven the way the outer tracker has been designed in terms of these module concepts. So the idea is to have some modules that are capable of rejecting signals from particles below certain PT thresholds, and these modules for the outer tracker are referred as the PT modules. So you can see from this sketch that the idea of these modules is that we'll have two single-sided sensors, which are closely separated, and they are read out by the common set of front-end ASICs. And the idea is that they will correlate the signals in these two sensors and select the hit pairs, which are called stops. And this will, the stops compatible with particles above certain PT thresholds, right? So the threshold thought is that around 2 GBs will give you huge reductions on the data volume, which will be sufficient to enable the transmission to the level one trigger. So these PT modules will have different sensor space depending on the regions of the detector. For instance, in the NCAPS disks, you will have a larger space between the sensors. Also, this PT module concept will, how can I say, relies on the fact that the strips, as you can see from the pictures, are parallel to each other. So with so to provide the measurement of this, yes, how can I explain? So to provide the to provide a measurement of the Z coordinate in the viral NCAPS, we will need a different type of modules, which are the PS modules. With, as I said, these modules, the PS, will be made by a strip sensor and a pixel and a micropixel sensor. So these are kind of combined hybrid, in the sense that you have one sensor in a strip and the other one in the pixel technology, and this is to have Z coordinate measurements in the parallel and the radial coordinate measurement in the NCAPS. So you can see here how these modules will be arranged in the different regions of the inner tracker. So for instance, you have the ladders in the TV-DOS, you have flat arrays in the TV-PS, and tilted in the tracker barrel PS, and also in the, and you can see these disk forms in the TDD. So next detector, next in these descriptions, CMS will be installing a new minimum ionizing particle timing detector, which the basic idea is that we will have a 4D measurement to try to assign, to distinguish between the different vertices. So the idea is to, I mean, the target is 30 to 40 picoseconds resolutions, and as I said, the idea is that we will be assigning the charge tracks. This detector will be helping in assigning the charge tracks to the correct interaction vertices. This MTD detector will provide timing measurements in the viral and the NCAP regions, and it will be covering the pseudo rapidity range from 0 to 3. This MTD detector will be placed between the tracker and between the calorimeter and the in some space between the calorimeter, and it will be placed between the tracker and the calorimeters. And as I said, you have the barrel layer and two end cap sections, which will be covering the total area from 0 to 3 in pseudo rapidity. So for the barrel, the technology that has been selected is a crystal scintillator, read by silicon photomultipliers. And well, this decision has been driven basically by the fact that both those crystals and the photomultipliers have been already proven to be radiation tolerance up to the fluences that we expect for the conditions at HL-LHC. And for the tracker layer of this minimum MIP time detector, the technology that has been selected is a low gain avalanche detectors with which are silicon sensors with some internal gain of about 10 to 30. As I said, these end caps will be instrumented of each side of the interaction region, so we'll have positive, negative end cap, and this will be made by two disk systems that will provide the 2 hits per track to get the timing measurements. So the 2 hits are really needed to achieve the desired time resolution of 30 to 40 picoseconds, as it is the target value. And again, this disk will be placed between the end cap calorimeter, the high granularity calorimeter, and the tracker, and there will be something like 3 meters from the interaction region. The end cap will be covering the area from the pseudo rapidity ranges from 1.6 to 3 to 3. So what about the barrel calorimeters? So as I said, these nowadays the ECAL is made of lead tungstate scintillating crystals, which are read out by avalanche photodiodes, and these active and these materials and electronics and readout electronics will be kept for the HL-LHC. So the only thing is that the crystals will be cooled or operated at lower temperatures to mitigate the increase in leakage current. But the barrel calorimeters will have an upgrade on its electronics, mainly on its electronics, with the objective to fulfill the trigger requirements and the trigger latency, which, as I said, it's going from 4 picoseconds to 2.5 picoseconds. And the level 1 trigger rates for 700 kilohertz compared to the 100 kilohertz nowadays. So for this, the front end needs to be replaced. And one of the things is that the new front-end electronics will allow to get information for single crystals, while the current electronics is only using at level 1 information from clusters of 5 by 5 crystals. So this upgrade will allow the trigger to do better matching between the electromagnetic showers and the tracks to provide a better oscillation better oscillation numbers compared to the current systems. So this electronics has been already tested during recently on test beams, and the results have shown that the new electronics it's meeting the HL-LHC requirements. For the hadronic barrel, similar as the electromagnetic, the plastic scintillator and the fibers, the wavelength shifting fibers will be kept, as the expected radiation damage of these components has been found to be negligible. in terms of the physical performance of the CMS. But the phase one front-end electronics, which consists of photomultipliers that has been already installed on the LS2, will also continue to be used for the HL-LHC period. And on top of this, both the the ECAL and the HCAL will have new back-end electronics. Next part is the high granularity NCAP calorimeter. So the existing forward calorimeter, which for the electromagnetic part is again lead tungstate crystals, will be replaced, and same for the the hadronic calorimeter, the plastic scintillator. Both these two calorimeters in the NCAPs will be fully replaced with a new combined electromagnetic and hadronic sample calorimeter, which will be primarily based on silicon sensors as the active materials. But also, it will also implement plastic scintillator tiles read out by the silicon photomultipliers, but these will be used at larger distance from the beam line on the hadronic section, as you can see from this figure here. So this is the sensor, the silicon sensor part. Here you have this scintillating plastic scintillator area, which is farther from the beam line. So the basic element, as I said, is this silicon sensors, or the right, yes. So some additional information: the new high granularity calorimeter will have more than 6 million channels compared to the 20K which are available in the present detector. The electromagnetic calorimeter will consist of 26 layers, where the active material will be copper and lead absorbers, while for the hadronic calorimeter, we'll have this mix of silicon sensors and scintillating tiles, something like around 240K channels, and they are arranged in 7 layers, which are all, these first seven layers are all made of silicon sensors, and 14 mixed layers, as you can see from here. So the basic component will be this the silicon modules, which will have, these are the active part of the detector, the active detector element, which is something like 160 millimeter hexagonal shape silicon sensor, which you can see from this picture. It will be sandwiched between some base plates of copper base plates, and we'll have the printed circuit board that will keep different electronics, and everything will basically build your silicon modules. You can see from these pictures how they are arranged. So we have that the modules are tiled on either side with a 6 millimeters thick copper cooling plate in yellow, which together with the base plates will be forming the absorb layers, and this will be alternated to form 2.1 millimeter thick lead planes, which will be clad with a 0.3 millimeter stainless steel sheets that will be placed in either side of the module, of the cooling module plates. And this each of these planes will be subdivided into 60 degrees units, which will be called as cassettes. These pictures from here, you have this arrange of modules putting together to form this cassette, which for the electromagnetic calorimeter will be 60 degrees units cassettes. And as you can see from the pictures, since you have both, since you have let's say two side layers, we will expect three layers of these double-sided cassettes to provide the full 26 sampling layers of the full electromagnetic calorimeters. So for the hadronic calorimeter, the absorber will consist on stainless steel plates, and again this will be somehow arranged in cassettes, but these cassettes for the hadron calorimeter will be 30 degrees cassettes, and you can see from these pictures this how had a cassette for the hadronic part is envisaged, where you have some part with silicon sensors, and the top part you have the scintillating tiles active material. So just to finalize, so these silicon sensors need to be operated around minus 30 degrees Celsius to keep sufficiently low noise on the electronics. Yeah. Next description. Next part is the outermost region, our CMS muon detector, which is the muon system. So the existing the phase one technologies were DTs in the barrel regions, CSCs in the end cap regions, and the RPCs covering both barrel and end cap regions. And the current chambers, the present chambers, will be operating during 10 years of the HL-LHC, but the detectors will be upgrading the electronics in order to cope with the higher rates and for the HL-LHC, and also to improve the overall performance of the detectors, right? So just as a summary, the DTs are going to replace all their onboard electronics and back end. The RPCs will be also replacing the off-chambers electronics and the back end, while the CSCs have already replaced during LS2 the front end boards and will also be replacing the back end. So the DT as an extra how can I say, well, just to say that the DTs are now in run 3 testing their new detector electronics. They have implementing one complete sector of the detector with the phase 2 electronics, which means they are using this new onboard electronics, the OVDT, and they have these prototypes working in parallel with the legacy electronics. So here are some of their results. So basically, they have measured that the phase 1 and phase 2 heat efficiency are 100% consistent, and that the measurement of the phase 2 trigger perimeters time resolution is also comparable to the offline resolution. So under the new conditions, the HL-LHC conditions, again, similar as in the pre-sync condition, most of the backgrounds and most of the muons are produced in the forward direction, which means a high pseudo rapidity, or in the end cap parts. So this currently this region on the CMS has not been fully equipped with all the muon chambers, which were foreseen at some point for the phase 1 design. So therefore, the forward regions will be completed with the missing muon chambers. And this will be done by adding new detectors in the forward regions using 2 technologies. The new gas electron multiplier systems that we have already installed the G11 during LS2, but new stations to increase the coverage will be coming. They are the G21 and the ME0, and besides that, on the last 2 end caps, the 3 and 4, the new improved RPCs will be installed. So I will just talk a little bit about the gas electron multipliers, as is the first detector for the HL-LHC, or for the first phase 2 detector that is already there. It's already installed and working. So this new technology, the gas electron multiplier, was introduced by Fabio Soli. And the GEM electrode is consists of a thin polymer film, metal coated on both sides, and pierced with a high density of holes of around 50 to 100 square millimeters. These foils are placed between a drift and a charge collection electrode, as you can see from here. And by applying the appropriate potentials, field lines and equipotentials are developed near the hole. So the large difference of potential between the 2 sides of the foils create large electric fields in the hole. So the electrons that are released in the upper region will be drifted to the holes and will acquire additional energy and will start ionizing more gas molecules, right? So a sizable fraction of these electrons are transferred into the lower section, right? You can see here from here, and they can be collected or by an electrode or even injected into a second multiplying region. This gas electron multiplier will have been selected as they are known to operate reliable at a high rate, at the order of a megahertz over a centimeter square, and to have excellent longevity, right? And well, just to keep in mind that the flux in the CMS end caps is not expected to exceed the 50 kilohertz over centimeter square. So this is why the decision to use this gas electron multiplier in the end cap region, where we expect the higher background conditions. So as I said, the CMS G11 station is already installed. It is based on triple GEM detectors, with a gas mixture of 70% argon and 30% CO2. These chambers are trapezoidals and can be as large as 1.2 meters long. The whole detector consists of 144 chambers, which are associated in pairs. We are calling them super chambers. And the installation of these all 72 super chambers has been completed in September 2020. We are now, GEMS are now participating in the run-tree data taken. And as I said, this is the first phase 2 detector that has been already installed, and it is operational on CMS. So one major improvement of having this G11 station is that we will be providing additional bending angle measurement. So the idea is that the CMS level 1 standalone muon triggering will be improved. So the G11, So yes, this G11 installation will allow us to measure its position adjacent in the adjacent G11 and the CSC M11 chambers will give good position resolutions, and this will provide a measurement of the bending angle, and we will be adding redundancy. And this is important as we will maintain the 15 GBs online thresholds on the level 1 trigger rate. As yeah. Yeah, sorry. The G21 project will be also installed in the second layer of the CMS Mion systems. This will be using the same technology as the G11, so triple gem technology. Now this disk will consist of 36 G21 chambers per end cap and will be organized into layers of 18 chambers. There are differences with respect to the G11. Now these chambers will consist of 4 G21 modules. There are 2 different types of modules to avoid the overlapping of the areas. So we will have 8 different modules, which are called M1 to M1 to M8, and the installation is planned to be happening during the year-end technical stop in 2023, between 2023 and 2024 for one of the end caps, and the other end caps will be installed in the following year, in the following year's end technical stop. But I have to say that the G21 mass production has already started in 2021. We actually have one demo chamber that has been installed in CMS in November last year, and well, this demonstrator chamber is using the final electronics, so it tested. So next, the next upgrade will be the ME0. This ME0 will be in the highest forward region of the Mion detector. It will consist of a layer stack of 6 triple gem detectors, 18 stacks per end cap, which will sum 36 total stacks, or something like 216 modules. These modules will be segmented into 8 readout partitions in ERA and 3 in 5. So we will be having 24 total readout sectors. This additional layer, which will be the 5th layer in the Mion system, will increase the coverage from 2 to 2.8 in pseudo rapidity. And again, this this ME0 will be providing trigger signal in the very forward regions, and also will be providing hits that will be used in the offline Mion reconstruction. So some of these requirements that this technology needs to fulfill are that we have to provide 97% efficiency. The rate capability has to be larger than 150 kilohertz per centimeter square. They have to be radiation harnessed, and the angular resolution should be less than 500 micro radians. So I said this ME0 detector will be positioned behind the new NCAP calorimeter, and will provide a measurement of the standalone trigger measurement and heat reconstruction for the forward Mion region. So just to finalize, there will be also the installation of the IRPCs on the last 2 end caps. This will extend the coverage up to 2.4 in the pseudo-purity. The addition of these extra layers will add redundancy to the ME3 and ME4. 72 RPCs will be installed in total. They are segmented into 20 degrees in 5. They are these chambers are 1.6 by 1.2 square meters, which are in arranged in trapezoidal shape. And compared to the old RPCs, the time resolution expected is 200 picoseconds, while the current RPCs are 1 nanosecond. So just to say that there are 2 production sites, and the production has also started. The first production site is Ghent, which has already assembled the initial quality control and prototypes in 2020. It has also produced 8 RPCs, the demonstrator RPCs that are on the already installed on the cavern. And the next step is that the Mexico production site has to be ready soon to start the production, right? So I will just finalize by telling you that this Mexico assembly site at Ibero is near ready to start assembling and testing chambers, the gas system, the HV modules, and the stations for the quality controls are already operational. So the ongoing activities are basically related to logistics. And the team members that will be participating in the assembling and testing will be trained again during chamber assembly, and some of them have already gained lots of experience in chamber-related activities during their stays at CERN. Final validation of this lab is planned for next year, and so next year the assembling in this site should be starting. So,
Mr. Raul, can you hear us?
Yes.
Yes, I'm afraid your time is over. Could you please just wrap up?
Yeah, I will tell you that if you want to have more information on all these upgrades, you have here the documentation for each of the subsystems. And I will conclude by saying that HL-LHC will be delivering up to 4 inverse attobarms. So CMS is undergoing a substantial detector upgrade to cope with these high occupancy and large radiation conditions. We have the first phase 2 muon detector, namely the GEM G11, and all projects are progressing on the transition from prototyping to production. So thank you very much.
Thank you very much. I guess we have time just for one question, one very urgent question, if anybody. Well, if not, thank you very much again.
Yeah, thank you.
Let's continue with the next talk. Dr. Sanchez. Oh no, excuse me. Sorry. Dr. Edgar Perez.
Yes, hello. Do you hear me?
It's your turn. You can start sharing your screen.
Okay, perfect. Thank you. Hello. Good afternoon in Mexico. Sorry, good morning in Mexico. I am Edgar, and I was a few years ago in the field of particle physics. Nowadays, I have switched to nuclear part, and I will, let me make it larger maybe.
We have a bit of problems to hear you. Could you get closer to your microphone?
Yes. What about now? Do you hear me? Sorry, maybe I can make the settings of my microphone a bit louder. And what about now? Is it better? Hello?
Okay, you can try. Let's see if it's fine.
Okay, let me know. I will try to talk louder. Sorry. Yes. So the content of my talk is I will start about a bit of my career in science in the field of particle physics. And then I will give you a bit of overview of the nuclear power plants in Germany, the challenges, the nuclear power plants worldwide, the decommissioning process that I work on. And at the end, I will talk about the projects I work on currently, which are SysTech and SAFE. So a few years ago, I was also in the field of particle physics. I did my bachelor and master degrees at UNAM in Mexico. For my master thesis, I did the measurement of the 5 resonance in proton-lead collisions at 5 teraelectron volts with the ALICE experiment. From these results, a paper was published together with the K-star resonance at the same energy. On the right side plot, I showed you just an example of the 5 resonance signal. The upper plot shows the raw signal with the peak at the correct energy. The blue dots correspond to the background. So after subtracting the background from the signal, one gets the plot below, where the signal is again fitted with a Boytian function, and some residual background is removed. From this plot, one can calculate the yield, and from the yield, one can get the transverse momentum spectrum as a function of PT. Here I show this is for proton lead and as a function of multiplicity. Yes, as a function of multiplicity. On the right-hand side plot is just the mean PT of the left-hand side plot as a function of multiplicity again. The A plot, this one corresponds to the K star, and the right-hand side plot corresponds to the phi. Here I show for different collision systems like proton-proton at 7 teraelectron volt, which is the green points, lead-lead at 2.76, which are the red points, and proton-lead at 5 TeV, which are the blue points. It was observed that in all cases, the mean PT was increasing as a function of multiplicity in all collision systems. That was one of the conclusions in the paper. After the master degree, I came to Germany to do the PhD in the Goethe University in Frankfurt. I changed the topic to instead of the resonances, I went to the transverse to measure the transverse momentum spectra and cross sections of charged particles in proton-proton collisions at different energies. From my PhD work, we managed to publish 3 papers. I just selected results from one of them, as you can see here in the plot. I show you the proton-proton transverse momentum spectrum, which are the black points, and to put together also the lead-lead spectra as a function of centrality. The proton-lead is also shown here in the green points at the same energy. One of the important results that I achieved during my PhD was to manage to reduce the systematic uncertainties significantly compared to previous results. And this helped in the way that we could calculate in a very precise way the nuclear modification factor. Just to give you a quick introduction, the nuclear modification factor is calculated as the ratio of the spectrum or the yield in a ion-ion collision divided by the yield in proton-proton collision. In the left-hand side plot, I show you 3 cases, and the red points correspond to lead-lead collisions at very central collision, 0 to 5%. The blue points correspond to a peripheral collision, 70% to 80%, and the green points correspond to proton-lead collisions. We can see that a proton-lead collision it's almost the ratio, the nuclear modification factor is almost 1. This gives the conclusion that the suppression that we see in lead-lead collisions in central collisions is not due to the cold nuclear matter effects, but rather to the partonic energy loss in the hot and dense quark gluon plasma created in this kind of collision. And it's a very similar case for a high PT in peripheral collisions. They reach unity. These results were also compared to other experiments like CMS. In the right-hand side plot, you can see the comparison. We compare proton-lead and lead-lead central collisions, and both experiments are in good agreement, but with the peculiarity that the ALICE results now they are very precise and very small systematic uncertainties compared to CMS. So after finalizing the PhD, the question came of what to do now, where can I go, where I can still use my expertise and my experience acquired during the PhD. The option was between continuing in science or industry. And I found that the best option for me was to go to industry. So in mid-2019, I joined the company SafeTech. It's a German company founded in 1993. It's relatively young. It's not a big company. It's a mid-sized company of around 500 employees. And we are focused in the field of radiation protection services, nuclear facilities, nuclear decommissioning, or in other words, it's just building down the nuclear power plants. Also the nuclear waste treatment and documentation, and nuclear waste disposal. Just to give you an idea of, before explaining the projects I work on, I need to give you put you in context of what is the situation with the nuclear power plants in Germany, and so you understand better the projects and their goals. In Germany, there are 23 power plants, but after the accident in Fukushima in 2011 in Japan, the German federal government decided to shut down all nuclear power plants, and the deadline was this year. This was, the government was afraid, and the population as well, to have an accident like in that, like what happened in Japan. Therefore, they decided they will go out of the nuclear power, out of the nuclear power production plants and in the form of electricity creation. So after post-operation, after closing a power plant, the decommissioning and dismantling must start. The goal is to clear the buildings and go out of the Atomic Energy Act, meaning that the area where a power plant was can be used for anything else, like a park or residential buildings. It would be safe to be used as for different purposes. It's worth to mention that the operators of each respective power plant, they are private companies, they are responsible for the commission of the operation, not the government. The government made the decision, but the operators need to implement it. And in the map here, this is the map of Germany. The points represent the location of each power plant. At the moment, there are still 3 power plants in operation. They were supposed to be shut down this year, but due to the energy crisis in Germany and Europe, they were postponed to be closed to next year. The majority of the power plants are in the commissioning and dismantling, and just very few are in post-operation. They are shut down, but they are still not in the dismantling phase. So what are the challenges of dismantling a power plant after shutting it down? So first of all, the first one is financing. It's a very financially, it's very costly to demolish a power plant, because every dismantling project has to be planned individually. Not what was done in one power plant can be implemented in another. Every power plant, it's unique. Securing know and how and maintaining the competence of the people who was working actually in the power plants needs to be kept. The approval times are usually very long. The amount of bureaucracy is very large. And how to proceed with dismantling? There are very kinds of dismantling, like for example, complete demolition, safe confinement, how to disassemble large components, and last but not least, the acceptance within the local population. Another challenging thing is that if the technologies and materials are available to perform successful dismantling, and who will perform the commission and dismantling from own resources, external contractor or external service provider are allowed. So these are like the main challenges for dismantling. How does it look worldwide? There are around more than 400 nuclear power plants in use. This is an image of 2016. The majority were located in the American continent, Europe, and Asia. And back then, there were 222 new power plants, nuclear power plants planned to be constructed. Most of them in Asia, especially China, South Korea, and Japan. They are betting strongly on the nuclear energy power plants. But all these power plants, many of them are very old, and they are almost reaching their lifetimes. The normal lifetime of a nuclear power plant is around 40 to maximum 50 years. So the power plants that were built in the 80s or late 70s are soon going for dismantling and decommissioning. So until 2030, there are plans. The projection is that Europe will have to dismantle around 160 power plants, America 71, and Asia around 60. So Germany is facing that problem now because of a political decision, but the rest of the world will follow just because of the time is reaching the the power plant's longevity limit. And how is the process of dismantling a power plant? So it's a very long process, can take between 15 to 30 years, being 30 the most likely number. Dismantling needs to be approved by the government. That can take up to 5 years to be approved. And during this waiting period, the nuclear power plant is shut down and post-operation starts. This means that dismantling of the control area is it's planned, and the used or all fuel elements are taken out of the reactor core, and they, like for example, in the picture I showed, here is a fuel rod being taken out and putting into small containers called castors to be stored in a different place and outside the nuclear power plant in a cooling swimming pool to be controlled with a good amount of security, of course. When the dismantling permit is granted from the government, two options are considered. The dismantling can follow two paths: either a safe confinement or a direct dismantling. A safe confinement, in this path, the power plant is completely sealed for around 30 years, but without fuel elements. They are removed, and then the power plant is sealed. The advantages of this method is that the contamination of waste is less time consuming due to the decay time. One simply just seal the power plant and wait until the short-lived nuclides have completely decayed. A disadvantage is that the timeline of dismantling is very long, longer than 30 years. The expertise of retired personnel is lost. The people who actually work in the power plant would have been retired by then after 30 years. So that knowledge is gone. In the direct dismantling, the power plant is dismantled after operation, which means that as an advantage is that the expertise is available, is still operating, directly involved in the dismantling phase. One can early use the area for other purposes. After building down the power plant, one can use it to build something else. And the German companies who are in charge of dismantling can for sure develop expertise, and which can be used somewhere else in the world, can be exported internationally. As disadvantage, the clearance and the contaminations are complex processes. And of course, due to the high radiation, makes it more complex that a human goes into the power plant and performs the dismantling. The danger of a high contamination in the body is high. In the direct dismantling, which was the method that the majority of the nuclear power plants in Germany followed, there are many phases. In phase one, the no longer needed systems are removed, like for example the flood water tanks, the pressure accumulator, the control rod guidance. And in phase two, the primary coolant lines are removed, the pumps and a steam generator. In phase three, only in this phase, the strong radioactive and contaminated components are removed, like the reactor vessel and the concrete shielding are put away. In phase 4, all remaining systems are dismantled, like, for example, the cranes and the ventilation or the wastewater plant are removed. In the last phase, one has the power plant practically completely empty. What is remaining is the buildings itself, the walls, the floors, and the ceilings. And is at this moment, in this phase, where my company plays a big role, and we use the projects that I will talk about to help in this process. The first project I want to talk about is SAFE. It stands for Software Assisterte In Situ Freimessen. It's an assistant software for in situ release measurements, and it helps to for clearance of buildings or individual rooms. This is a picture of where the reactor was actually present. Here one can see the hole where the water tanks were located. One can see a closer picture here. One sees that there is no even electricity, nothing. The structures put there are just for for security, so that the persons do not fall into the holes and have an accident. But to achieve a safe decontamination of the nuclear power plant, one needs a digital version or to be able to work it in a computer. To achieve that, my company performs a digitalization of the complete power plants. You can imagine that 30 years ago, 40 years ago, digitalization was not as commonly used as nowadays. So we use, for that purpose, we use 3D laser scans in order to get a complete mapping and digitalization of the power plant. So this is what a digitalization of a room would look like directly from a 3D scan. We get a triangle mesh of all the surfaces in the room. But what we actually need is something more human readable to handle a good operation. So we have developed an algorithm in the company that converts this triangle mesh into something like a grid or a lattice of a desirable size, as you can see in the right-hand side picture. This algorithm also detects which is the room that actually is being scanned. For example, it can distinguish when the door belongs to which rooms, and it is not confused by the room behind that door. But how do we decommission a room or a building? So we need detectors. These detectors are the perfect ones are the in situ germanium detector, which is this one on the left and on the right. The germanium crystal is in the front, the front of the detector, and for its operation needs to be cooled down with liquid nitrogen. You can see the tank in the back. And this on the right-hand side, you can see it that to perform measurements and to reduce the background, we make use of collimators in the front, covering the detection crystal. This is not a big detector. It's like the size of a big small suitcase or a big backpack, but it's not so, due to the liquid nitrogen and the heavy lead collimators, it is not so easy to manipulate. Therefore, we have structures to be able to move it around more easily. One of the advantages of this kind of detectors is that it is allowed to be a room temperature between uses. One needs to cool it down to be used, but for example, in the weekends when the operator is not gonna perform any measurement, it is allowed to be warm up. On the contrary, other detectors, gamma detectors that need to be kept in constantly, need to be cooled down constantly. Another advantage of these kind of detectors is the excellent energy resolution when applied to gamma ray spectroscopy. This very good resolution is in the range of 50 keV to 2 MeV. And on the picture, I show you a comparison between germanium detector and sodium iodine detector. And you can see that the peaks are clearly distinguishable in the germanium detectors, and we only get very broad peaks in the other one. This is very important because we need to distinguish between the gammas coming from certain nuclei like cobalt or cesium that need to be kept under a certain limit to be in order to be able to release a room or a building. This is actually complete digitalization and an example of how the software together with the algorithm works. The other advantage that of this kind of detectors is that we can cover a large portion of area and perform short measurement to acquire already good results. In the upper picture, I show you an example of a detector measuring around 20 to 25 square meters. This grid is 1 meter by 1 meter. And we have also developed an algorithm that optimizes the positioning of each single detector inside a room, so that it takes the least amount of measurement time and the least amount of measurement performs to be able to release the whole measurement. To be able to release the whole building. This algorithm is based on evolutionary algorithm that is widely known nowadays for many applications. The results would be as it follows. When the major part of the room is releasable, meaning that it's below the contamination, the radioactive contamination is below a certain threshold given by law, it can be demolished and can be recycled for other purposes. The concrete can be used in other purposes. And for example, in this case, the red part would have a high activity, then it needs to be treated as a waste, radioactive waste that will have a different treatment, of course. Ultimately, what we achieve is a complete mapping, or yes, a complete mapping of the of the power plant where the activity is located, or the contamination of the surface is large. But what happens to the dismantled material? Well, 97% of it's recycled. Only 3% it's treated as a waste. The 3% is the one that has high radioactive contamination, and it needs to be disposed, stored, or have a kind of special treatment. There are three paths for this waste: either to be treated as clearance or as conventional waste. Can be given to another control area for recycling, or be treated as radioactive waste and be stored underground. This is the most expensive way of treating this kind of waste. And for that purpose, we have our next project in the company to help in this kind of problematic, which is the SISTEC, Simulated Integrated Gamma Spectra. That's what it stands for. And what we use is as a detection system is a large clearance monitor, which is 24 plastic scintillator detectors surrounding a sample that is like I show in the picture. The large clearance monitor would look like this: 4 detectors per face surrounding the sample, trying to cover the whole 4 pi angle, solid angle. The advantages of this system is that it can detect very low activities in a very short measurement time. Like with a couple of minutes, we could have already a reasonable good result. And one can measure up to, in these kind of containers, up to 1 metric ton of material. This material can go from concrete, metal, plastic, sand, or liquids, like a liquid barrel can go inside, and some other materials that are present in the power plant. But the major problem of this large clearance monitor is that it cannot reconstruct exactly the location of a hotspot or a pond-like source that is inside the sample. As you can see, the detectors are quite large. They are approximately 50 by 50 centimeters, square centimeter. So the resolution is not so good. The best idea would be to increase the number of detectors to have a better resolution, but that is not possible. So what we did is to use what is already being implemented in medicine. We created an algorithm that is inspired on what is SPECT and PET. In the first one, the SPECT, one injects a radioactive substance in living tissues or in a body, and one measures the photon emitted from this substance. In the PET, positron electron annihilates and emits 2 photons in opposite directions. One uses an algorithm to reconstruct this the image, as you can see on the figure. One used this coincidence of the photons emitted to reconstruct a good image of the inner part of the body. So what is the difference between medicine and our algorithm, which is called conditional entropy maximization, CEM? In medicine, one injects, one detects, creates the imaging, and does the analysis. In our case, we have already the radioactive substance inside, present in the sample. Our algorithm makes the image and provides the activity of the sample. The image of the radioactive contaminated source is reconstructed by the means of maximization of the information entropy. And as I mentioned, the CEM is not only an imaging technique, but also a way to estimate the activity, which is in the medicine case, it would be not so important, but for our purposes, it's crucial. So the CEM equation, it looks like this. It contains several parameters and that needs to be provided in order to run. It has not a closed solution, and thus we solve it numerically. And one of the most important parameters is the cell detector efficiency, which is the probability of a cell in the sample. Of course, we create a grid in the sample, we discretize our sample, and we calculate the probability of a cell I of emitting a photon and being detected in detector J. These efficiencies we calculate using Monte Carlo n-particle, widely known as MCMP simulation. And we can also estimate the activity and the position of gamma emitting radioactive sources. I will give you an example of how good the algorithm performs. For this, we make use of a cobalt 60 point-like source, each with 5 kilobecquerel activity. Just as a quickly reminder, the cobalt 60 decays into nickel 60, an excited state of nickel. And the nickel, by going to the ground state, emits 2 gammas. These 2 gammas are later detected and assigned as a proof to of a cobalt source present in the sample. So for the example, we need to divide our sample in 3 layers: bottom, middle, and top, each of around 20 to 25 centimeters wide, and we make 2D projections from above. So on the left-hand side is the bottom, the middle side is the middle of the sample, and on the right-hand side is the top. So we have put 2 point-like sources. This is the original distribution, one in the bottom and one in the top. And this would be the reconstruction of our algorithm based on the on the information that we have provided, the count rates, efficiencies, and some other parameters that are special for each power plant. With this kind of algorithm, the hotspot can be identified, and also the activity of them. And this helps in the way that the hotspot can be removed and the rest can be releasable. And this, of course, optimize the way the waste is treated. It's much more efficient to just remove a small part where the activity is present. I just want to mention that there was an episode from John Oliver about the nuclear waste. He talks about, this is an episode of 5 years ago, he talks about nuclear waste in the US. And this is just a clear example of how the politicians sometimes make decisions without the good information. And it shows that the US currently, or at least it was 5 years ago, that they had no idea what to do with the nuclear waste. And as you saw in my graph before, North America is one of the largest regions with the most amount of nuclear power plants in the world. So in the near future, they will have a serious problem. And now coming to my conclusions, the commissioning of nuclear power plants is a very complex and challenging process. We have at SafeTech, we are developing state-of-the-art solutions to help in this process. One of them is the conditional entropy maximization algorithms, who precisely locates hotspot and provides the activity of point-like sources in waste packages. This algorithm also provides a faster and more efficient separation between what can be released and what cannot, what needs to be stored underground. The other algorithm that we have is SAFE, that helps to modernize and optimize the building decommissioning process. And this process can be done from within SAFE, from the power plant digitalization to measurement optimizing the results and reports. And this is with the help of using innovative technologies and algorithms. Yeah, thank you very much. That was my talk.
Thank you. Thank you very much. Now it's time for questions. Questions, anyone?
I had a question around slide 42. When you do these measurements about the activity in the room to decide which part to go to this kind of
To the like this.
which kind of precision on the position you have. Let's say you have a scanner spotted some areas. Do you have a trial or do you have several process to keep safety there? I mean, it's 1 meter.
Yes, that's a very good question. We have a positioning system inside the room that I did not talk about. We have in each corner positioned, and of course each detector has a tag or has a emitting signal that a device that emits signals to record the position inside the room. And this device is precision. The precision of the positioning is around of the order of millimeters, if I recall correctly. So of course we have an uncertainty of a few millimeters in the positioning that needs to be taken into account, of course, at the end.
Any other question? Well, if not, let's thank the speaker again.
Thank you very much.
It's time for coffee break.
Hola, Ivonne, ¿nos escuchas?
Hola Mario, ¿cómo estás? Sí. ¿Me escuchan a mí?
Te escuchamos muy bien. Entonces,
Ah, perfecto.
por favor.
Ok.
Ok, perfecto, sí se ven.
Ok. Entonces nada más voy a...
Hola, Ivonne.
¿Qué tal? ¿Cómo estás?
Welcome everyone. Let's talk about the core corona model. Ivonne, please go ahead.
Okay, thank you very much, David. So, hello everybody. Today I want to present some analysis that I am doing in collaboration with another people, Alejandro Ayala, Isabel Dominguez, and Marilena Tejeda Germans. And the title is to present this core corona model to study the hyperglobal polarization within the multipurpose detector at NICA. So as a first, very fast introduction, the study of heavy ion collisions at the lower end of the QCD phase diagram, that means this region, has become recently a topic of great interest because we expect that the transition from hadronic matter to another in which quarks and gluons are deconfined be a first order phase transition in difference that the thing that we expect at higher energies, like the energies that LHCN experiment does. And also we are interested in studying the hyperon global polarization because this help us to characterize the strongly interacting matter because different hydrodynamic models relate this variable, the polarization, with the vorticity, the viscosity, and also the flow. So the principal idea is that in non-central heavy ion collisions, like appears in this drawing, we have a very large angular momentum. And the vorticity that it's in the direction of the angular momentum, it's going to be also in the direction of the polarization of the particles because due to the spin angular momentum coupling, so the particles are going to be polarized principally in the direction of this angular momentum, and it's going to help us to measure, or a tool to measure, the vorticity in the system. And also we are interested in measure the polarization on from the lambda particles because the way in which they decay, that it's a parity violating weak decay, and it's very easy to measure the polarization just measuring the angular distribution of the protons that, or the baryons that came from the particle, from the decay. So one of the important things is that recently several experiments measure the polarization that appears here in this plot on the left. And the thing that they found is that the polarization increases as the collision of the energy of the collision decreases. Also, the most recent results made for ADES experiment at the very low energies, almost near the threshold limit of energy to produce a lambda particle in PP collisions, shows that the polarization increases. So also this related with the fact that previously a transport model, the URQMD, predicts a peak or a maximum of the vorticity at low energies, tell us that it's very important to analyze what is happening in this region and also check if it's possible that we found this peak in this part. And NICA experiment, it's a nice tool to analyze what is happening here because it's going to run at this energy domain from 4 to 11 GBs. So there are several models trying to explain hyperon global polarization, but in particular, I want to show these two that are related with the model that we developed that appears on the right, because as our model that looks on the plot on the right, it describes the data very well from BESS experiment, and also it describes the higher polarization of the anti-lambda shown by data, and also the new values of data, the new values of data predicted by STAR at 3 GBs of energy. It's not the only model. We have this 3 fluid dynamics model that also predicts a peak, like appears here. And these are, it chooses a different equation of states to try to describe this behavior. And the maximum is near also these 3 GBs, more or less. And the other model, well, the problem of this model is that doesn't describe the difference between lambda and anti-lambda. And other model is this Jurgen-Lee model, in which they assume that the lambdas came from different freeze-out regions, and that different configuration of the source from which lambdas came from produce that the anti-lambda polarization be larger than the lambda polarization, like appears here. However, there are no results yet at low energies. So the principal ingredient of our model is that the peaks that appears here are modulated or linked with the relative abundances of lambdas coming from 2 different regions in the collision. So the principal idea on this core corona model is that when we have the collisions of 2 ions, like appears here on the drawing, we can differentiate between two regions with different density. One of these regions, it's going to be the core in which the density is higher. The particles are going to be produced through reactions like occurs in a QGP, in a quark gluon plasma. And in the corona, in which the density is smaller, we are going to have processes that produce particles similar to the processes that occurs in the nucleon-nucleon interactions. That means by recombination like processes. And then the total quantity of particles that are produced is given like the addition of both contributions. So this is not the only time that the people use this model, because this idea has been used before to describe other variables and other observables. Between of these are the centrality dependence of strangeness, and also to measure the centrality dependencies of the elliptic flow and the mean PT that appears here in these two plots. So the principal idea here is that the different variables are fitted with a function like appears here, in which one of the contributions of the variable is given by the particles on the core multiplied by the fraction of particles in that region, plus the contribution of the other region. Normally, the variable in the core is considered like the value measured in the very central collisions, and the corona is estimated with nucleon-nucleon interactions. So keeping this in mind, so we develop this model in which, considering the principal definition of the polarization, that it's defined like the number of particles with a spin in some direction minus the particles with the spin in the opposite direction, we can use this idea to separate both contributions, and after some algebra that, because of the time I'm not going to explain here, we can rewrite an expression for the Hyperon global polarization like appears on this chart on the left. That depends in some variables that are very easily to measure from experiments and also for calculations. So this polarization depends on the polarization of the particles on the corona, the intrinsic polarization C and C bar, the ratio of the particles of the lambdas that came from the core region with respect to the particles that created in the corona, and also the ratios of the antiparticle to particle in the 2 different regions, in the corona and also in the core. So as our first approach, we assume that this polarization from the particles that came in, that are produced in the corona, it was 0, because we thought that the nucleon-nucleon scattering is not enough to align the spin in the direction of the angular momentum. So when we want to, the results give a good result, as I showed you before, but when we want to analyze the new data as a function of centrality, we notice that even the polarization is well described for the first centrality, for the most central collisions, we cannot describe the thing that happened in the most peripheral collisions. And also, is something that happened with the three fluid dynamic model, can only describe until 30% of centrality. So we continue working with our model, and the thing that we found is that maybe the problem is that we cannot say that the polarization in the corona is completely zero. Because when we check the value of the polarization in experiments of proton-proton collisions, we found that this value for different energies is completely different from zero. It comes from 25% until 40%. So that means that this term that we decide to remove, we shouldn't do it. And when we just add a value, an arbitrary value, we can see that change the behavior for higher beams of centrality in our prediction. So the idea is that, considering the definition of the polarization or the way in which it's measured with respect to the angular distribution of the protons that came from the lambda, and given by this expression in which depends on the asymmetry, the chi parameter, the polarization of the particle, and the angle between the proton that came from the lambda with respect to the, the angle with respect to the angular momentum in the lambda rest frame, that we know that it's also rewritten with flow techniques to give this expression in terms of the even plane angle and the resolution of this angle, and get this expression. So we can use this expression to try to analyze what is happening with the contribution of the polarization in the corona. And then for that, we need to assume that the polarization that it's measured in proton-proton collisions is a thing that we call transverse polarization, that it's not measured with respect to the angular momentum. It's measured with respect to the perpendicular to the production plane of the lambda, that it's described by the direction of the beam and the direction of the lambda itself. So then, doing some calculations and assuming that the direction of the beam is parallel to the z-axis, we can express this component or this normal in terms of the transversal components of the momentum of the lambda. And doing some algebra, introducing in the angular distribution like appears here, and also following the same method to rewrite the polarization in terms of the even plane angle and the azimuthal angle. So then we can rewrite using the method of momentum that it's here that I'm going to explain because of the lack of time. So we can get this expression that appears here that tells us that the transversal, the transverse polarization measured along the direction of the angular momentum, it's going to be related with this this mean value of the cosine of the angle between the azimuthal angle of the lambda and the even plane angle. Solving this transverse momentum polarization gives us this expression. But also that we need to notice is that this value that appears here, we can say that it's going to be different from zero. And also we can compare with the value of the global polarization measured normally. And we can see that, yes, it's going to be a similar, something that it's that can contribute, but also it's going to be a smaller quantity than the value given by the hyperon global polarization. Besides, also, when we remember the how is written or how we express the direct flow for different particles, we can see that it's similar to this term. So we need to ask, and we need to continue trying to know and explain if it's possible that this contribution of the transverse polarization be related with the value of the direct flow. But this is still work in progress. Also, now we need to know how we can estimate that in the experiment. For that, we need to separate the contribution of the particles that came from the core and also from the particles that came from the corona. To do that, we are implementing the URQMD model that allows to separate the number of particles that came from the core and the number of particles that came from the corona. producing that only, doing only a fluid dynamic evolution of the particles that came from the core. Also, it's possible to choose different kind of equation of states. In particular, to apply this method, we need to choose the equation that gives us the confinement and also the chiral phase transition. Also here, it assumes that there is a smooth crossover between the chiral hadronic, the chiral hadronic part and the other part of the system. Also, the thing that we like about this model is that it's possible to separate both regions with respect to the density, not the density of the nucleus like in our model, but see the density of the quarks that are in the region, selecting by some in some slices of pseudo rapidity and measure the number of quarks, and then comparing with a critical density. So, keeping this in mind, we did a small simulation in which we produce particles that came from the core and came from corona and secondary particles. That is a distribution that appears here on the left. We can compare the plot on the empty markers is all the lambdas, and the full markers are the lambdas that came from the core. When we get the ratio between these contributions, we can see that it's almost a 50%. This is not exactly the thing that we calculate in our model with the Glauber model. However, it helps us to try to reproduce and estimate if it's possible to reconstruct some contribution of the local polarization to the global polarization. For that, we choose an arbitrary value of 40%. We add this polarization only to particles that came from the corona, and choosing the direction of this polarization parallel to the normal to the production plane. And then we are using the MPD root framework to transfer this polarization to the particles that are decaying from the lambda. This work and these tools was developed by Elisaveta Nazarova and Vadim Voronuk. And they are proving that it's possible to measure global polarization for PHSD, as shown in the talk of Victor Ryabov that gave yesterday. And then after that, that we have this transport of polarization, we can realize the reconstruction of polarization. And what we get? So when we get just the polarization for the lambdas along its direction of polarization, we can see that it's a perfectly 100% or 1. When we try to get the local polarization of particles with respect to its normal, to the production plane, we can see that it's 40%, that it is a good agreement with the thing that we expect. But when we want to get the local polarization in the full sample, that means the particles that came from the core and also the particles that came from the corona, we can see that the value of the polarization decreases almost to the half. This has sense because the half of the particles are without polarization because we choose in this way. So we expect from this that if we get polarization from particles, it's going to be an effect of the global polarization, but could be smaller and diminished because of the polarization of other particles. Then, when we analyze this as a function of the centrality, we only analyze the backward region, and we can see that the polarization it's almost 2%. So it's really too small compared with the 40% that we chose at the beginning. And when we consider all the lambdas, not only the lambdas in the corona, this falls until 1%. So contribution from corona particles looks to dilute due to zero polarization of the cores and secondary lambdas. So we can expect that this polarization really affects the value or the dependence on centrality. We don't know exactly because the polarization and also the effect at lower energies could be a little bit different with respect to these energies. So we need to continue working on this direction in order to increase the sample to analyze, this data, and also to prove with another energies and choose a better way to get a polarization in PP collisions. So I'm going to summarize because this is very fast. So the thing that we show here is that the core corona model is used to describe the hyper and global polarization. It describes very well the data and covers the energy range from ADES to star and NIC experiment. it shows that local polarization could contribute to global polarization with a fraction of the value of the transverse polarization measured in PP collisions. URKMD has been used, and it does a nice work. It's possible to do this transport through MPD route, and we show that can contribute the local polarization to the global polarization, but still is work in progress to say it's something that we can say that it's true. Thank you very much.
Thank you very much, Yvonne. Can you help us?
Yes.
The problem with the presentation?
Oh my God.
In the last minute.
So, what can I do?
You see it as you're sharing it?
No. It says that I am sharing, but it doesn't look like I am sharing, so I can try to share again. So, can you see it? So you didn't see anything.
We could hear you all the time, just in the last minute during your conclusions.
Aha.
We will try to respond.
Okay. Well, maybe show very fast. The thing that I show you, this is the model that we are using, the URKMD model, that if you see, it's possible to separate the core from the corona. This green line tells us which is the energy of the density that we are choosing. With this simulation, we can get this distribution that appears here, in which part of the lambdas are from the core and the other part from the corona. The ratio is almost 50%. It's not the thing that we want from our from our model that we developed using the Glover model. But the result shows here that when we try to reconstruct the polarization along the direction of the polarization vector, it's 100%, the thing that we expect. When we analyze only the local polarization, give us the 40% also that we expect. But when this is going to be diluted, when we consider all the lambdas, the value is almost the half to 20%, because it's related with the percentage of lambdas that came from the core, that the polarization is 0. And the results that we have here for polarization, the global polarization from the lambdas in the corona, the errors are very big, but the value could be thought that 2%. When we consider all the lambdas, it decreased to 1%. So this is not this is work in progress. We cannot conclude anything yet, because the polarization also at this energy, that it's 9.2 GeVs, is small. But this is like a good start to get the contribution from the polarization. Okay, so I try to summarize.
Thank you. So, ask somebody questions. Somebody.
Can you hear us, Yvonne?
Yes, hello.
Related to slide 8.
Yes. Slide 8. Yes, sorry. Can you repeat me the question?
The question is, how do you think can improve the model in order to reproduce better the higher centrality?
Okay, one of the things that we start doing is that first, the model that we use, that is the Glover model, get a critical density to produce the quark gluon plasma. And this critical density, at the beginning, we use like a step function that is not true. is not the reality. So we try to change this step function, doing more soft, and we increase a little bit the number of particles that are produced in the core for higher centralities or for bigger impact parameter. But this is not enough to reproduce all the data. The second part then was to introduce this polarization from the particles in the corona that, as appear here in this plot, we can see that just adding an arbitrary value give us a value. I mean, it's different from 0 for the most peripheral collisions. In this example, we add just a 4%, and exactly appears that it's a 4%. So this is the idea why we are starting to try to introduce some value for this polarization to the particles that came from the corona.
Thank you. Thank you again, Yvonne. Need to move on.
Thank you very much.
Thank you so much. Hi, everyone. I'm glad to be here and have this opportunity to share with all of you some progress of my bachelor thesis that is called Effective Interactions of Yukawa and Universal Textures, and working with Dr. Lopez Lozano and the Dr. Pauline Cancavila, and we are from Universidad Autónoma del Estado de Hidalgo. So I divide this presentation in 4 sections. Have the introduction, I talk a little bit about our model, our results, and finally the conclusion. Okay, as an introduction, I want to talk a little bit of the tool that we uses in particle physics to describe all the phenomena in the nature, and the standard model. And the standard model is a H theory that unifies 3 of the fundamental forces in nature that are the strong, and the weak, the electromagnetic force, but don't include the gravitational force. This theory uses the fundamental particles to describe the phenomena, and we have 2 kinds of fundamental particles. And the first one is the fermions, that also divided into 2 kind of particles. We have the quarks and the leptons. The first one also are divided in up type and down type. And the last one are divided in charged leptons and neutral leptons. And in the other hand, we have the bosons. And these particles work as intermediates to communicate the forces. We have the photon that leads the electromagnetic force. We have H gluons and the G 0 and W. Okay, so, and I forget that we have also the Higgs boson. Okay, this theory is able to predict a lot of experimental data, but there are so many troubles to predict from others. And this theory uses the Lagrangian formula to, to communicate that direction. We have the Lagrangian density for standard model. We have 4 sectors: the gauge sector, color sector, and the Dirac sector. And the last one is the Ikawa sector. And the small spoiler, we are working in the last one. So, talking about the things that standard model could not predict, and it is a very important experimental data that is the neutrino masses. A picture of Super Cavalcante, experiment that show us that neutrinos have masses. And in the other hand, we have the dark matter. It's another prediction that the standard model could not give us, and are very strong, very strong data that there are the dark matter. And another phenomena that is not predicted is the hierarchy of masses. We have a marked hierarchy for the masses of fermions. It is a pattern that maybe is something, it is telling us something. Another thing that understand better nature, the part of certainly very important that journey the theory that we have now, and some questions that we have formulated, that is why we have the hierarchy on the matrix, what is the mechanism behind that, and if all the parameters on the flavor sector are arbitrary, or maybe could we have a connection. And yeah, as I said, we're gonna work in the Yukawa sector. We have this Yukawa Lagrangian, and we see that there only have a term with left-handed neutrino, but according to the experimental data that the neutrinos are not massless, we need to introduce a term. Well, this is a way, but we need to introduce a term that bring the mass to the neutrino. So the first thing that we gonna do is add this term. We right-handed neutrino and some terms that will be Majorana masses. We don't work with those terms. Our first approach was only with Dirac masses. So with adding this term, we can solve the problem that neutrino are not mazeless and the standard model can predict the meshes. But we have a trouble because the experimental data don't show this right-handed neutrino. So we have the hypothesis that this neutrino could be this higher scale. Well, we can consider the terms of Lagrangian. For who predict or the mazes the neutrinos. It has been formed. Okay, so the way that we think that these right-handed neutrinos will exist is with an interaction with some other particles that could exist also in a higher energy. So we proposed an extension for the standard model and that introduced particles of Flygon type and right-handed neutrino. And this is inspired by the Frege-Nielsen mechanism. Okay, so we have the Lagrangian, the Yukawa effect, the electronic vector, the Yukawa, where we have these terms that we should. And yeah, and the last. Okay, so we proceed. We propose an Yukawa matrix at high energy, such well with that form, and we take the Bacon expectation value in order to get the Yukawa matrix of the standard model. This Yukawa matrix of high energy has the interaction of these scalars that we want to propose. CL and C right are scalar fields that transform a triplet flavor in the fundamental of SU. And this is the form of the field. Okay, and we have to rewrite the Lagrangian density for the electronic sector. And we have that. And in this way, we can see that these flavors, these particles that we propose, interact with the fermions, well, at high energy. The denominator of the exponential is the scale where or particles can sit. Well, proceeding by the main equation, we take the fluid form in the Yukawa matrix of high energy, and we apply the Baker-Campbell-Hausdorff formula, and we have the form for the Yukawa matrix. So the next step is to take the Bacon expectation value, and we can have terms of the Yukawa matrix that we are looking for. So the next step is just to prove that our model could be viable, and we compute, we make code in Python that could generate the Yukawa matrix, and we use random parameters to explore possibilities of that mazes that to generate the green mazes. And we use a chi-square parameter to filter our data. The data, the experimental data that we want to reproduce with our model is this one. The square mass is different from the neutrino, the neutrino is naked. And well, we find that this model and this stage will not predict the observables that we have in the experimental data. We see that the chi-square is very big, and well, this is for the first one, the 3-2, and for the another one, we see that we could fit with the 2-1, but in the another, and we don't fit with the experimental data. So what's the conclusion? What is needed to improve this model? Well, we see that maybe adding the terms of Majorana or using genome mazes will help us, because in fact we don't have a reason to ignore it, but it seems to be more easy. But well, not pretty today. And we want to conclude that the introduction to structure of flavor and tip to generate this Yukawa matrix, and it is possible to demonstrate that could exist common mechanisms to generate the texture that is valid are the metrics of the paradigm. Thank you.
Thank you very much. So it's time for questions. Questions, everybody?
Thanks, it was interesting. I have a question about the value of the scale lambda psi.
Oh, yeah, just we don't fix and scale at this point. We just work with the mechanism to generate, because the experimental data that we want to reproduce is different from the squared method. So these different doesn't change if we do the scale. Yes.
And do you have any idea why the chi-square is so large? The chi-square is really huge.
Yeah.
So I mean the model seems to be sensible. So why it is so large?
Yeah. Yeah. Something that I think is important to by my point of view is that and it makes sense that this could work because this is the mechanism that we find the particles taking higher energy level, finding the particles that will show it. How it works.
And again, on lambda psi, I agree to what you said that in principle it doesn't matter because it's a combination of numerator over this lambda psi in the denominator. But yeah, but exactly, I think that this application of the Baker-Campbell-Hauser formula requires that lambda psi is somehow large. Otherwise, we agree on that, right?
Yeah. More question? Well, if not, let's thank the speaker again. Hey, Miguel.
Well, good morning to everyone. My name is Miguel Angel, and I'm going to present some of the results from my thesis research in the Instituto de Física, supervised by the Victoria Miguel, present here. So let's begin. First of all, we have to present of the low standard model, but as everyone have already shown of the main some of the main features, I'm going to skip into the important part that I want to show you. At first, I would like to highlight the Lagrangian, which is well known that is composed by four sectors: the fermion, the gauge, the Higgs, and the Yukawa sector. This will be useful in the more later. As we know, the standard model, of course, is not the final physical theory. We have at least a lot of problems that are not solved. I am distinguishing two kinds of problems: the external phenomena and the internal issues. That's what I call. For external phenomena, of course, are the ones that are not included in the standard model. For instance, the gravitational interaction that is not included, massive neutrino, of course, and dark matter. And for the internal issues, one in particular is the main motivation for this investigation, which is the free parameters problem. As you may know, and depending on the author, we can see even 19 free parameters in the standard model, which have to be determined experimentally. So for these two problems, we have taken two approaches. For the free parameter problem, I'm studying a method called reduction of coupling that I'm going to explain in the next slide. And for the external phenomena, we're working with the multi-Higgs problem. So this method proposes that for a given model with n
coupling parameters, we can express every couple as a function of one of them that we are going to call the main coupling that I call lambda 0. And to achieve this goal, we are going to use renormalization principles and renormalization group invariance principle. So the first condition is that the renormalization group equation, also known as beta function, must fulfill the renormalization group invariance. This means that in the Hallan-Szymanczyk equation have to be fulfilled in this new reduced system with one only beta function. So taking that in account, we can get the reducibility condition, sorry, which relates these two equations, giving us a system of equation that actually this beta, it's the same that the beta equation from the main coupling. This will give us n reduction equation that are ordinary differential equations that we have to solve in order to get those functions we are looking for. In order to achieve also the idea that we express these couplings with just one, in function of just one of them, we have to take another condition, another physics. One of the ones that asks this model is the weak coupling limit, which says that in the limit when the principal coupling go to zeros, all the couplings have to go to the zero as well. And including this with the renormalizability condition, we have to find a solution given us a power series of the main or the principal coupling, as you can see in this equation. Of course, I have said the relational coupling model is one of the goals that we want to achieve is to attack the free parameters problem. These have been made in the past by the group working on Kubo, Siebel, and Zimmerman in the mid-80s, actually. And they get, of course, they found Yukawa coupling constant value for the top hit, for the quark top and the tip and in the Higgs boson, predicting before the discovery of these particles, the masses that I show here. I'm going to discuss later about the accuracy of that prediction. So as the standard model have been explored with this method, the work I want to develop is exploring on the multi-Higgs method. And some of the motivation is the ones here are going to pass a little faster all the time. So it's known that it's one of the easy extensions to implement. The notion of generation can be brought in a more natural way. And of course, a lot of phenomenology can be brought through these models, like several Higgs, flower changing neutral currents at tree level, additional CP evaluation forms. And of course, one of the attractive ones is that proposal give us dark candidate matters, like these dark Higgs. So how do you implement the multi-Higgs models? I told you that this Lagrangian would be useful. The modification have to be done in the sectors where the Higgs particles are, or the Higgs fields are present. So this is in the scalar sector and the Yukawa sector. So this is the formulas that I have to use. And for this particular talk, I'm going to show you how it works for the two Higgs doublet model. So applying this equation, we will have the potential, this potential, and the Yukawa Lagrangian expressed like that. Of course, this is too large, and using the uh, conditions that I have right in the last slide. We can write in the more general way that is used to be presented. One of the in the title of this presentation, I talked about reducing complex into Higgins double model with natural flavor conservation, and what this means is what I'm going to explain. I have mentioned that one of the main complex of multi-Higgs model, in particular two Higgs doublet model, is that we can have a three-level flavor changing neutral currents. So a two Higgs doublet model can be divided into the ones that allow this three-level neutral current and the ones that doesn't allow it. For going with the phenomenology, we are like to avoid these three-level FNCMs. So for this, we can use the Paschal's theorem. And practically, we can get it by introducing a discrete C2 symmetry. And with that, we get the models called natural flavor conservation models. And the four types, and the non-four types of the Higgs doublets model. For this work, I analyzed all the four types of two Higgs doublets model to see what kind of reduction we can get. This model in particular is taken from the work for Denner. The original, the general potential is reduced by introducing the C2 symmetry, eliminating these two terms, and additionally, for avoiding the soft breaking of the symmetry, this term can be eliminated too. And we're going to have these conditions. For the Yukawa sector, the Paschal's theorem, I'm going to call it like that, just allows to the quarks to couple to just one kind of Higgs. So that's why I'm presenting this equation where you can notice that just for convention, the up-type quarks right-handed just couples to the second Higgs. And here, depending of the type, being 1 or 2 or X or Y, the Higgs that will couple to the leptons or down-type quarks are going to be mixed or different. So I'm going to, sorry. For this model, I have this BEPS, and the masses I'm going to obtain is that. So I'm going a little faster. Here what you see is the renormalization group equation of beta function for the different couplings I'm going to try to reduce. In this side, you can see the gauge coupling constant beta function. I highlight the Yukawa coupling beta function and the quartic beta function for the Higgs self couplings. So using the reducibility condition, we can relate each one of these beta function in this differential equation in a way that I take the strong coupling like the principal coupling, and the other ones will have to be a function of this one. So applying some magic, we are going to go to the reduction equation that are those ones. Particularly, these are for the type 1. The type 2 are another set of equations that have to be solved. And of course, this talk won't give me time to
explain how it solved all of the equation, but uh, for the at least for the gauge couplings, I can show you that I assume that we are going to have this power series solution. So I take them the first, the main, the leading order of this series and introducing into the differential equation and try to find the values of the main of the leading order. So here I present the two-gauge coupling reduction, and we can see that here only trivial and negative values were obtained. This means that we can just take the trivial one because a negative one would mean that the coupling is imaginary. In this case, we have two solutions. The positive one would be useful, but would mean that the weak coupling it is stronger than the strong coupling. So this coupling will be discarded too. So going to the result. For the gauge couplings, only trivial solutions are physically acceptable. So the function will be given as this one. And I found that for all the types of two Higgs-Doppler models with NFC, the lepton Yukawa couplings have to be 0 too. For type 1, the non-trivial solution are the top Yukawa coupling given as this function, and for the lambda 2 Higgs self-coupling. And for the type 2 and type Y, I found this function like the solutions. What I do with this function is to use an experimental value of the main coupling given with the strong coupling constant as that, and computing the value in the equation and getting the constant values. With that, I obtain these masses. Of course, as it's not determined the depths, so I can just give it like a maximum that can be obtained. For the type 2 and Y, these are the results I get. And I'm going to go to the conclusion. So the reduction of coupling method is presented as an attractive tool to deal with the pre-parameter problem. And I have mentioned, although the preliminary results seem not to agree with phenomenology, this doesn't discard the method, because as we know, the models that I tested are not the final one, and other particles and couplings might help to get best results. Actually, the motivation for doing this is because in the past, Dr. Mondragon's researches in minimum standard model have given more accurate results. This is a suggestion. Sorry. This is a suggestion that the method can be used as a testing tool for QFT model symmetries. So through this method, we find symmetries in the models. And given the given the physical possibilities of multi-Higgs models, it's interesting to keep the search for these models using the method. So that's all for me.
Thank you. I like a lot your explanations, particularly Pascos et al.'s theorem. It was also quite nice, so I like it a lot. Also, I appreciate that in your solutions, there seems to be quite symmetry for the results. And your values were the same or some opposite than others, things like that. So there was like an underlying, perhaps an underlying symmetry. Seeing this, maybe if you go to things that are more complicated, like 3 fixed doublet models or whatever, then perhaps everything can match. And the fact that there is this seeming underlying symmetry could help you in these cases where you would have more parameters. I don't know if you have thought about this, or is going to extend to even more extended scalar sectors.
That's a question that I was asking for. Thank you. So I didn't mention it, but these results are for level approximation, even in the masses and even on the solution of the equation. So actually, yes, and some of the papers that I read it and work with, the solution have to include, for instance, radiation correction, or as you say, some more symmetries that are not taught in the principle. For this example in particular, for this model in particular, I began with the assumption that the C2 symmetry have to be present in order to get experimental values, but in principle we shouldn't do it. But working with the type 3, this means the general one would be a little difficult for this level at least. So thank you for the question.
Thank you very much for your amazing presentation. I was just wondering if is there any physical reason for looking for one single main parameter, or is there any reason that we cannot take 2 or more degrees of freedom in your equations?
That's another excellent question. In principle, any of the couplings can be the principal one. I actually tested the being the main coupling, the weak and the electromagnetic couplings. And the reason I choose the strong one is because it has, what do you say? I forgot the word. Pre-asymptotic behavior. This means that the second principle mentioned is fulfilled. So the coupling goes to 0 when so the main coupling goes to 0 and the other coupling have to go to 0 too. But in principle, you can choose any of the couplings you want. I hope this answer your question. Actually, that's something I mentioned too. This is just one part of the investigation. They are called partial reduction. That when we can take all the like a dependence on 2 or 3 couplings, but the main idea is to reduce the pre-parameters. The one is the main goal that we have. And well, maybe you didn't notice, but we weren't able to fulfill the complete reduction. So one of the solutions we can take are solving the general equation and taking experimental values for different couplings and implementing this as on the function. And with that, we could have a function, as you say, depending on 2 or 3 parameters.
Okay, let's thank the speaker again.
Hey, good afternoon.
On for the laptop.
Can you hear me?